Hello physics students. Today I'm going to begin our video with a demonstration. So what I have is a kettlebell that I've modified, and I've drilled a hole in it and put a bolt through it. And I also have a cement block that's used in construction as home foundations, one of the many uses. What I'm going to do is I'm going to take this 45-pound kettlebell, but it's a little lighter than 45 because I cut the handle off. But I'm going to attach it to this cable over here. Okay. Steel cable that's attached to the ceiling beam over here. And there's a pulley, so there's nice low friction here. So I'll just attach this safety screw. Okay, so now what I have is what we call a pendulum, swinging back and forth. And so what I'm going to do is, let me stop this. In the first demonstration, I'm going to put this cinder block right here. And we're going to observe what happens when I lift this pendulum up and let it swing into the cement block. So I'm going to lift it up to approximately chin height, and I'm going to let it go. So, ready? Here we go. Okay, pretty dramatic. The cement block, which holds houses up, holds buildings up, stood no chance against this pendulum, this steel ball coming down, swinging down, smashing into it. The next demonstration I'm going to do is I'm going to set the steel ball against my chin, okay? And no, not down there. Of course, we know what would happen. But I'm just going to lift it up, and I'm going to hold it carefully at my chin, and then I'm going to let the ball go, okay? It's obviously going to swing forward and then swing back. So let's see what happens. So notice I didn't flinch. And that's quite a steel ball coming right at my face, and I am not flinching. And the reason why is because I know the topic for today, which I'll explain in a minute. But first, I want to give you a chance to see this demonstration. So I'm going to reconfigure the camera. Obviously, I can't have you here because you're at home. But what I'm going to do is set up the camera, and I'll lift the ball up to the camera. And if you want to see what it looks like, hold the screen nice and close to your face, and then you'll see if you have the ability not to flinch. Well, obviously you know it's not going to hit you through the screen, but you'll get the sense of how intimidating the ball really is. Okay, so here we have the ball, the steel ball, 45 pounds. I'm going to put it right up to your chin, okay? So, ready? Here we go. Did you flinch? Well, hopefully not, because you have as much faith in what we're going to learn today as I do, the law of conservation of energy. So what I'm going to do now is set up the camera again to the chalkboard, and then I'll explain the physics behind what we saw. Okay, so what was this idea that made me so confident that I was literally willing to bet my teeth on the idea? That idea is the law of conservation of energy. Now, you've learned this in chemistry or maybe even a science class earlier, and in most earlier classes, they state the law like this: energy cannot be created or destroyed. But in physics, we generally don't like to say it that way because it's not as clear as this. This captures the concept better and more thoroughly. The total energy of an isolated system remains constant. Not any energy, not like kinetic energy or PE. Those can change. It's the total, the summing up all the energies, whatever are in a particular system. If that system is isolated, nothing goes in or goes out, then the total energy remains constant. And we don't mean just mechanical energy like the things we studied. By the way, this is a term that you have to be familiar with in the Regents, this idea of mechanical energy. Mechanical energy is a combination of the three kinds of energies we already studied: the kinetic energy, potential energy gravitational, potential energy spring. We mean all energies, like we studied thermal energy on one of the days, but also chemical energy, nuclear energy, solar energy. All those energies together in a system are conserved. The total remains constant, not just these pieces, but all of the things. So now let's try and see how I knew the pendulum would not come back and hit me in the chin by looking at the energy dynamics or the changes of the energy as the system evolved. So this is a conceptual example. I have the pendulum drawn in 4 different positions. This, I made up a number of 10 joules of potential. I had more than that when I held it up against my chin, and no kinetic because it was at rest. I was holding it. So how do I know there's no kinetic, students say often? 1/2 mv squared. Look at the formula. And then the formula will tell you if it's 0 because velocity is 0, so we know kinetic energy is 0. So I let this thing go. And remember, this energy cannot be created or destroyed. Well, look, kinetic energy, the potential energy went away. So was it destroyed? No, they're talking about the total energy. So again, this way of saying it is better. So we lose the potential because how do I know I lost the potential? PEG equals mgh, assuming it reaches the very bottom down there. Then h is 0 and mgh is 0. Okay, so I know I have no potential. Do you know what the kinetic energy is at the bottom? So I'll pause the video, give you a chance to think and see if you could come up with the answer. Okay, so hopefully you said 10 joules because you are using this idea. The total energy has to remain constant, so we still have 10 total down at the bottom. How about over here when it's swung up a little bit, so it's gained a little h in mgh, but not the full original. So I'm making up a number. Maybe it has 2 joules of potential energy. Do you know what the kinetic would be at that point? I'll pause the video and give you a chance to come up with the answer. Okay, so hopefully you said 8 joules. How do I know 8 joules? Well, again, I started with 10 total energy, so I've got to have 10 total energy at all later points, okay? And then when the pendulum gets to the far extreme, if it gets to the same height, I have 10 joules of potential. Can you tell me what the kinetic energy is at the other side? So I'll pause the video, give you a chance to come up with the answer. Okay, so hopefully you said 0 joules. And if you did, you would be correct. 10 total here, 10 total here, 10 here, 10 here. The total energy of an isolated system remains constant. So that's how I knew my chin was safe. I lifted the pendulum up with a certain potential energy, and I held it there. I let it go. Now, let's say it had 100 joules of potential. So it swings down, loses the potential, gains kinetic, and then goes back to potential. When it comes back, kinetic, and then starts losing kinetic and gaining potential, I knew it could never go higher because then it would go 100 and then maybe it goes to 105, hits me in the chin. I know that's not possible because it only had 100. It cannot suddenly have 105. It can only come up to 100 and that particular height that corresponds to 100 joules. So I knew it was perfectly safe because of the law of conservation of energy. Now, of course, if I let it go and I gave it a little nudge, now I'd have 100 joules and maybe like 5 kinetics. So I have 105. And then when it comes up, it'll go to 105 potential. 100 potentials here, 105 is here, is going to hit me. So I had to really let it go at rest, okay? But it doesn't work as you would think, that it would just swing back and forth like in this example. What I'm going to do is reconfigure the camera, and I'll show you the pendulum again, and we're going to watch it in sped up time, and you'll see something happens as it's swinging. So give me a moment to reconfigure. Okay, so I have here this very massive pendulum, and I'm going to let it go against my chin as before, and then we'll see, and I'm going to now, see this doesn't hit me again, and I'm going to now speed up the film. Hopefully I figure that out at home when I'm editing, and then we'll see something after a minute or two has gone by. Okay, so. Okay, so as you can see, the pendulum has lost considerable height. So it started here, and so then basically now when it comes up here with zero kinetic, the potential, if say it was 100 here, now it might be only 80 or something like that down here. So does that mean the law of conservation of energy is false because this system lost energy? The answer is no, because the system is not isolated. That's the key. The total energy of an isolated system remains constant. If you were standing there instead of me, you would feel a nice little breeze every time the pendulum came up. And so what it was doing, it was sloshing the air and giving the air kinetic energy. That energy then that goes into the air as sloshing or eventually thermal energy had to come from somewhere. It came from the potential energy of me when I lifted it with my body and let it go. Also, that pivot up there is not frictionless, not perfectly frictionless. So every time it goes, there's a little rubbing and a little bit of heat. So it's, quote, losing energy. That system is losing energy, but the overall universe is not, okay? So it's still true, the law of conservation of energy. All right, so that's one point. When it looks like energy is not conserved in the system, it's because some of the energy leaked out or came in from the outside. So let me reconfigure and let's move on with the rest of the notes. Okay, so now what I want to do is a couple calculation examples using this principle or this law of conservation of energy. So here's one example. This is actually the example that we just did with the pendulum swinging, a 20 kilogram pendulum released from rest 1.5 meters above its lowest point. That data is about what appropriate to the pendulum I held against my chin and about how far it swung down. We're going to determine the kinetic energy at the bottom and the speed at the bottom. So it turns out that if you don't know the law of conservation of energy, students will say, okay, I know kinetic energy, let me go to the reference table and look for that formula. And the formula is, well, I left my reference table over there. So basically it's K equals 1/2 mv squared. And then they get stuck because they say, I don't know the V, so how could I answer that problem? Because you have to realize that it's an energy conservation problem. So we're going to use the energy at some other point to figure out what the energy is when it's kinetic. So as I always say when I'm solving these problems, I'm going to say it again and again, I strongly recommend drawing a diagram. In fact, on some tests, if you were here in person taking tests, I require a diagram and I take points off if you don't create one, because it's critical to organizing your thoughts. And it doesn't have to be a complicated diagram. I just draw the object in the what we call the before and the after positions. So, and then I ask myself 3 questions in both the places. So I'm going to ask 6 total questions. The first thing, does the object have kinetic energy at this point? And the answer is no, it does not. Again, people say, how do I know that? The formula tells me. Ke equals 1/2 mv squared with no velocity. V equals 0. That means the kinetic energy is 0. So no kinetic. Does it have potential energy spring? Well, that's an easy one. There are no springs there, so it can't have potential energy spring. And then, does it have PEG? And the answer to that is yes. Again, people say, how do I know that? Well, it's got a mass up high. So, MgH, you have it. So I write down that we have, PEG. I ask myself the same three questions in the second position, the after position. Ke, PEG, PES. Does it have Ke? Yes, it's swinging as we saw. It crashed into the cement block and destroyed it. So that has kinetic energy. How do I know that? 1/2 mv squared. Velocity, mass, yes, you've got kinetic energy. Obviously no spring energy because there's no spring. Does it have PEG? No, it does not. How do you know? PEG equals mgh. Without an H, you don't have PEG. So those are the two energies involved. And then what I could do is I could set them equal to each other. Energy before equals energy after, right? That's the law of conservation of energy. Energy can change. You could lose one kind of energy as long as in the system another kind comes to replace it. So we lost this and this replaced it, so the law is good. Energy is conserved. So again, I cannot calculate this, but I do have mgh. And so if I plug these in, I'll have the kinetic energy because I'll have the PE here, that is the kinetic energy. So plugging in the data, so the mass is 20 kilograms. G is 9.8. And the height was 1.5 meters. And if you punch that on a calculator, you get the answer of the kinetic energy being 294 joules. Again, that was the PE, which is the kinetic because energy is conserved before or after. Okay? So the next thing we want to know is the speed at the bottom when it's swinging. What did it hit? What velocity or speed did it hit the cinder block with? Well, now that we know the kinetic energy, we could look up the formula on the reference table for the kinetic energy, and that's Ke equals 1/2 mv squared. So the kinetic energy, 294. The mass, 20 kilograms. And V is unknown. So this is 10 right here. I'm going to divide both sides by 10, and I get 29.4 equals V squared. Square root both sides, and that comes out to 5.4. So there's the speed at the bottom. Amazing thing. The law of conservation of energy makes predictions that you can test, and that's how you know the knowledge is true. We could swing it, set it up, and see, and if it's 5.4, boy, that is an amazing law that can make that prediction. The other thing I want to point out is the law of conservation of energy is redundant because it's derived by Newton's laws. You could figure out the acceleration and then through calculus figure out the velocity from Newton's second law, and you would get that same answer. But boy, is that a very difficult calculation. So the law of conservation of energy is redundant, but it gives the answers very easily without intense calculus, just as you see, a little algebra. Well, I'm having fun, so I'm going to do another example. I don't know if you're having fun, but I hope you are. So, one more. And the reason why I want to do one more example, because this is a common mistake a lot of students make when they do a few of these problems. They think, oh, I know the law of conservation of energy. That's easy. PE equals KE. And it's not always true. You've got to derive this formula every time, a new formula with a concept, as the next example will show. So what I have Okay, so there is the example. We got a spring with a constant of 200 newtons per meter, and I'm going to compress it down 0.2 meters, and it's going to launch a 100-gram mass straight up. So I take this, and it's resting on the ground, and I crush this spring with a little ball on it maybe, and when I let the spring go, it pops up and the ball shoots up into the sky. And then eventually, as we know, when things launch up, they go to a maximum height and they come back down. We want to know that maximum height. Okay, so once again, we begin by drawing a very simple diagram, okay? Every problem, I recommend this. So here's the spring crushed. See, that's it. Don't have to be nice fancy coils. There's the ball, and then boom, it launches and rises up to some maximum height. So do you remember what we did in the last example? Well, hopefully you remember it. We ask ourselves 3 questions in the beginning and 3 questions for at the end. Okay, so the 3 questions are going through the mechanical energies that we have. Do we have kinetic energy down here? And the answer is no, because kinetic energy is 1/2 mv squared. There's no velocity, no kinetic energy. So no kinetic energy. Do we have spring potential energy? Yes, we have a spring that's either crushed or stretched out. And as we learned in the spring potential energy video, that means you've got 1/2 kx squared. So we do have PE spring. Do we have gravitational energy at the bottom? The third question, the answer is no. mgh is the formula for PEG, and h is 0 down here. Okay. Same 3 questions. Ke, PEG, PE spring. Okay. Do we have kinetic energy at the top? No, we do not, because when something reaches maximum altitude, V is 0, 1/2 mv squared is also 0. Do we have gravitational energy? Yes, we do, because we have mgh. We have a height for a mass. So we have PEG. And lastly, do we have spring energy? No, the spring is down here and it's open and relaxed. So x spring displacement is 0. 1/2 kx squared is also 0 then. Okay, so now we use, after we ask the 3 questions before and after, whatever energies were yes before and after, we now say the law is that the system doesn't lose any, so we basically have the final PEG that came from the original PE spring. And we can fill in what these are, these formulas. PEG, as you know, if you go to the reference table, it's mgh, as we learned. PE spring, you go to the reference table, 1/2 kx squared. Okay? So now we can plug in our data. Here's a little trick though. 100 grams, masses have to be in kilograms in these formulas. So we convert that to 0.1 kilograms. G is 9.8 meters per second squared. H is what we're looking for, so that is our unknown. Now, the 1/2 K, this constant, spring constant, is 200 newtons per meter. And the X is 0.2 meters. Okay, so now we just have to do a little algebra to solve for the H. So 0.1 times 9.8 is 0.98 H. And then if you multiply all this out, you'll get 4. And if you divide by 0.98, you get that this little ball rose to a height of 4.08 meters. So there it is. The law of conservation of energy tells us how high this ball will actually rise. Okay, so let me create a little pause, allow you to catch up if you need to. So that is the big topic for today, the main point of this unit. It finally came that energy is conserved. What does that mean? It means that sometimes you could lose energy as long as you gain another kind. Said another way, the total energy of an isolated system remains constant. As we saw here, we lost one, gained another. Again, sometimes you have PE going to kinetic energy. Sometimes you have PEG going to PES. So the law of conservation of energy is not a formula. It's a concept that generates a new formula for every single problem. Sometimes the formulas are the same, but that's by chance. So what you have to do, again, is ask yourself 6 questions, the same 3 in the beginning and end. Do we have KE? Do we have PES? Do we have PEG? Lay out all the yeses, and sometimes you have more than one. We're going to look at examples like that in the next video. Ask the same 3 questions. Do we have PES? Do we have PEG? Do we have KE? Write down which ones the answers are yes to, and then put beginning and end equal to each other and solve. That's the law of conservation of energy. Well, I hope you enjoyed yourself. I enjoyed smashing cement blocks and holding the thing up to my chin. Great drama in today's video. So again, I hope you enjoyed it, and I'll see you in the next physics video.